All right, well, hello everybody. My name is Erik Garcell. I work at a company called Classic, and I couldn't agree more with some of the last comments made during that panel that innovation is needed on the software end of things, but I'm biased because I work for a software company in quantum computing doing exactly that. So in this talk, we'll be talking about operationalizing quantum computing, and what does that even mean, right? At a high level, when I talk about operationalizing quantum computing, what I mean is it's the practice of developing, scaling, and deploying quantum workflows that are hardware agnostic and integrated with classical infrastructure, ultimately aligning with the mission needs of what you're trying to do. Now, I give a lot of workshops at universities. I do a lot of talks at enterprise client locations. So I see a lot of the gaps that are missing when it comes to realistically deploying quantum computing, getting beyond a basic hello world kind of example. There's many different hurdles. There's many different hardware approaches without a clear winner in the industry yet. And there's a huge gap between deploying a small bit of code and learning quantum computing and actually doing something impactful or solving a real sized problem. There's multiple integration paths if you're worried about connecting with HPC and actually doing a hybrid algorithm in practice. There are a lot of clients are worried about vendor lock-in, right? If they learn how to work in Q#, they're worried about being stuck in only Microsoft's ecosystem. What if they also want to try out, Amazon's ecosystem or IBM's? So there's a need in the industry to explore multiple hardware modalities without being stuck in this. And since I give a lot of these talks, sometimes I give some of these phone clicker questions where you can answer questions, interactively and engage the audience. And I find that typically, this was a conference I gave a talk at PERC, computing conference, where I'm seeing things like the major issues for their hurdles in adopting quantum computing and going into it and deploying it are things like there's too many algorithms, it's too difficult to explain, right? Hardware matters too much, bad documentation for any software. You know that's always going to be an issue if you don't document your things well. Lack of visuals, lack of access to the hardware. It's difficult for users and practitioners to realistically use quantum computing. And when I look at that, I see two main issues. There's issues on the software stack, on tools available to end users, and then there's also issues on the education side. So when I think about enabling quantum computing and operationalizing quantum computing from a software end, it's important to know where quantum computing is today, how most people use it and deploy it. So if you're unfamiliar with quantum computing, if you're coming to this event trying to figure out kind of what it looks like and how it's deployed, it looks a little bit like electronic design. It looks a little bit like assembly language when you're coding this out, where every one of these white lines you're seeing on the bottom graphic is a qubit, or kind of the equivalent of a single bit, and each of the blocks on there is a Boolean operation on that bit. And this is the quantum assembly language. This is what's going to get translated to hardware level, and this is what's going to get executed on that hardware. To program that out, you have to actually define every operation on every one of these bits or an operation between them. So it can be quite intensive to program this out for a large number of computational bits. And certainly once you get to about 30 or so, it becomes quite untenable to program this at the gate level. You're certainly going to miss one of these blocks somewhere, and your whole code's going to get destroyed and not operate the way you intended to. So kind of programming at this Boolean logic level isn't tenable for large-scale applications, and certainly nothing that's going to be operationalized, nothing that's going to bring value to an end client, nothing that's going to be used in production is going to be 20 qubits, 30 qubits. So programming at this level doesn't facilitate the use of the technology. So when I think about operationalizing quantum computing, I think about three key ingredients when you're looking at tools and resources to use as an enterprise on deploying this. Whether you're looking at it for production or internal use or skill building, you need to look at abstraction, scalability, and you need to look at portability. It needs to be tools that help you develop problems from the problem statement, not from a qubit standpoint. Scalability means that you can look at your problem and your code that you're developing will scale as your data input grows, not having to make bespoke quantum programs for every new data set put into it. And portability, that means that you can have access to multiple hardware vendors. You can deploy your quantum code despite it being an IBM or an IonQ or a QEra machine, so you can use multiple hardware modalities and benchmark quantum computing for your applications. Now, when it comes to the education side of things, most of the education when it comes to quantum computing is very physics-oriented. That's the lens that physics education began from, and that's where it is at many universities. education on quantum computing from this standpoint is phenomenal, but it largely stops at a hello world example at the end of that education. When you're hiring on for quantum talent, most of the talent gets hired from students who've worked on research projects on quantum computing. They're not learning the skills to build realistic application-solving quantum algorithms in the classroom. They're learning it in lab projects, working with professors. And universities are starting to move towards this regime where they're starting to teach their students how to actually build quantum algorithms, how to actually build out these workflows. But it's important, whether you're at a university, whether you're working on workforce development, to look at it from an engineering lens more than just a pure physics standpoint. Right? It's great to have the intuition on quantum computing, but you need to move past that. Like electrical engineers, when you take a computer science course on this, you might take one course in Boolean logic and then not touch Boolean logic again. Then you learn higher level abstraction layers. I think the same thing should probably move to quantum computing. It's important to know the gate level, how to rotate a block sphere and what that means in the underlying hardware, but most of the education should come from higher level languages, should come from figuring out how do I build applications and really deploy something that makes sense. So when I talk to universities and figure out how do we build education plans, how do we teach these students, and not just the PhD students working at, learning at community colleges, trade schools, they want to figure out how do I learn this new quantum computing program. It's quantum computing. As a computer scientist, I should probably learn what this is. A lot of students have this drive to learn this technology, but it's quite untenable to learn about it when you're starting from a physics standpoint. So teaching quantum computing as an engineering discipline is a new framework that a lot of universities are starting to look at, and a lot of workforce development plans are also starting to look at. And it enables students to not just design, qubits and layouts. You learn algorithms and not just gate manipulation or qubit manipulation. So what we do certainly at a lot of universities too is help out these universities figure out what that lab practicum side of the computing course looks like. Often universities and workforce development, there's workshops and they'll give you a lecture, but rarely is there the hands-on portion that tends to be attached to this in computer science courses. You need to have these students actually coding and producing something at the end of the day. So we work with a lot of different universities to perform these and have these workforce development plans put in place so that students can work seamlessly from concept to application, building real and scalable quantum algorithms and learning these skills in the classroom instead of having to rely on finding a professor in quantum computing to help them gain these skills to then work in a quantum workforce. Now, when I talk to a lot about this at universities and workforce development plans, we always try to model essentially pipelines, right? We want to make sure that you're looking at this from a problem definition scope, following that into modeling your solution. So you always look at what is your problem, how do you scope that out, what is it mathematically? You model that out on your quantum system, you compile it, and then you benchmark it. A lot of times, quantum code is developed, but there's no benchmarking. It stops at, I made the code, I'm good. What do you do with it? How do you analyze it? What are you comparing this with? There's not enough on the end user aspect of these things that needs to be deployed. So when I look at operationalizing quantum computing from an educational standpoint, I think about two guiding principles if you're concerned about deploying actual quantum computing in production. You have to think about building quantum computing from concept to craft. Learners need to move beyond just qubit intuition and some physics intuition. They need to learn how to build fully scalable quantum algorithms applications. And you have to build these applications with a purpose, not just a theory or fun graph theory problem. A lot of these students don't know how to abstract or what these problems can solve. You need to look at it from a telecommunications network problem or an electrical grid network problem to learn how you take a real world problem, map it down to the mathematical framework, and then compute that out. That's what these industries are looking for. They want you to take a problem and for you to figure out how do I map that down to the mathematical framework and code it out at the end of the day. So there's quite a few areas of quantum computing where operational quantum computing is an absolute must. You're not going to get anywhere on 5 qubits. We talk a lot with state governments and federal agencies and government contractors. And certainly when I talk to state governments, I see 3 main needs from their perspectives. They want to showcase quantum computing to the businesses in their state as well as the investors. They want to de-risk quantum computing to those investors and businesses, show them a reasonable path to success. What are the time horizons on different quantum solutions? How do you get there? What are some case studies of other industries and pathways that have done this? They want to educate quantum computing as well, right? Not just for the PhDs, but for their technical colleges, for the community colleges. And once they're trained, they want to retain that talent in the state. They want to make sure that you keep this talent within, because keeping the students and the talent brings the businesses, and keeping the businesses brings the students. So it's a little bit of a chicken or egg, but how do you start these engagements? How do you start these communities to retain the talent and bring these businesses in-house? Now, federal agencies, they're wanting to de-risk investment by ensuring portability across platforms. They want to do benchmarking, they want to evaluate their test case across multiple hardware vendors, but it's quite a bit of a hurdle to tell their developers to learn Q# and Qiskit and Circ code. Not a lot of managers are going to allow their engineers to learn 3 different programming languages to evaluate quantum computing. So having higher level abstracted languages and tools helps to de-risk quantum computing. Having the right tools available to you to enable this makes it a much more affordable, much more time savings endeavor to go ahead and explore this technology. They also want to explore the time to impact. They want to see what that time to impact is. They can read all the Boston, McKinsey, Boston Consulting computing reports, McKinsey reports saying what the time horizons are, but they want to have more of an internal intuition on this. They want to know for certain applications, what's the resource use, how many qubits do I need to do X application, so that they can verify that and build that internal competency in themselves. And government contractors are quite in the space of wanting to connect this with HPC stacks. They want to make sure that they have these data flows across their HPC systems, because at the end of the day, quantum computing is going to be part of the HPC stack along with CPUs and GPUs. And at the end of the day, they want to deliver solutions that are hardware agnostic, because they don't want to bet on a winning horse too early. They don't know which hardware modality at the end of the day is going to win, so they want hardware agnostic solutions to develop their code on so that they can work on it and make sure that they're not wasting their investment at the end of the day. Now, we work with many clients helping to deploy operational quantum computing and help them build this out. Now, like I said at Classic, we're a software development platform for quantum computers. We're doing exactly what was talked about in the finance talk earlier, which is, or the investment talk earlier, which is the innovation of quantum, making it an easier solution to deploy your quantum code and create quantum pipelines. I won't talk too much about the product itself, so feel free to come to our booth if you want to know about that. But largely, we help these clients to do a number of things. We've worked with BMW to build out large-scale quantum algorithms and deployments. Not just toy problems. We did an algorithm called QSO, or quantum simulation-based optimization. They wanted to figure out solving the unit commitment problems for essentially piping the cooling and optimizing the cooling system of their engines. We also worked with a company called Intesa Sanpaolo, a bank out of Italy, to educate and build out their quantum computing workforce. Mitsubishi Chemicals on benchmarking different quantum software applications across different hardware vendors. Actually, the photo there, with Intesa Sanpaolo, a fun one. We won second place in the algorithm award for IEEE. It was a fun one. And actually, a newest partner of ours, you can actually see them in the Innovation Center, enabling, they're doing quantum accelerated digital twin platforms, using our platform to deploy and benchmark different hybrid quantum classical finite methods on our back end. So actually, if you want to take a look at them, they're up in the startup ecosystem. And just to wrap it up, if you're looking at operationalizing quantum computing, if you're wanting to go ahead and deploy this, there's kind of 3 aspects I would say to look at. You want to make sure that you have tools that are scalable, hardware agnostic, and abstracted. And you want to focus on workforce development and training that's engineering focused and workforce and pipeline focused. And of course, it's important to find the right partners in this quantum ecosystem to help you navigate different time horizons for quantum computing and focus on solving the right kinds of problems for what you're investigating. Thank you very much.